Hey guys, and welcome to Sound Waves. So earlier we talked about the difference between longitudinal and transverse waves. Well, sound waves are a type of longitudinal wave. So that means that they travel parallel, and we're going to look at some examples of how that works. The first example of sound waves that we're going to look at to kind of describe this is the sound that we make when we talk. Do you guys remember how earlier in the year I completely lost my voice for like a month and a half? Well, my vocal cords quit closing, and because they quit closing, they weren't able to vibrate and create sound. So sound being longitudinal waves, when we speak, our vocal cords vibrate the air and set it into motion. And what that does is it makes the air molecules vibrate in the same direction as the vibration of your vocal cords. So we're making sound, we're talking, it's vibrating the molecules, they're bumping into the next one, and moving and propagating that sound forward. So if we look back at our example, you imagine sound waves kind of like the slinky. As our vocal cords are opening and closing and sending molecules of air, sending little packets of sound over, little waves of sound out in all directions. As molecules get pushed, they become more dense in that region, and this increased density pushes the molecules in the neighboring region further ahead, and they move and move and move, causing sound to travel. Another name for this is called compressional waves. So let's look at some examples of what this looks like in terms that you're more familiar with sound itself. To help me out with that, I have a few different tools. The first one we're going to use are tuning forks. So tuning forks, when you hit them, they send out sound waves. So right here, I have a tuning fork that is A, and it's sending out about 426.7 waves per second, going back to what we learned about waves earlier. So one more time. I want you to notice a few things about this tuning fork. First of all, as I bring it closer and further, what do you notice about it? Hopefully one thing that you noticed is that it gets louder as the source is nearer and quieter as the source is further away. This is something that you're probably quite familiar with. If there is a bird that's right outside your window, it's going to sound much louder than the same bird a few houses down. Sound is much louder the closer you are, and it kind of dampens out the further away you get. To demonstrate this idea of frequency and pitch even further, we are going to use a sine wave generator that is hooked up right here. So what we're going to do is, if you'll notice, when the frequency is low, so about 1, right, we have one wave or one peak per second coming along. But as I increase the frequency, we have more peaks per second. Okay, but now I want you to listen really carefully. As I increase the frequency, listen to what happens to the pitch. So do you hear that right there? At 150, this is our pitch. We keep going. Here we have 300 hertz, 500 hertz, 700 hertz, and 800 hertz, which is where we cap out with this machine. So frequency determines the pitch that our ears hear. Just to quickly remind you, going back to our first waves lesson, frequency is equal to 1 over the period. Period being how much time it takes for one wave to travel from one peak to the next peak, which is in seconds. So our units for frequency is 1 over seconds, which is recorded as hertz. The last thing that we're going to talk about today is a really cool phenomenon called the Doppler effect. You're probably quite familiar with it. You hear it anytime an ambulance comes by, or a lot of times when cars are passing by, you can hear it, or airplanes. Let's watch this video clip from YouTube to see an example. Notice as the ambulance is approaching, it has a much higher sounding pitch. And as the ambulance is leaving, it sounds like it's a much lower pitch. But how does this make sense? Because it's not like the ambulance is like, oh, we're passing this done right now. Let's change the pitch on our ambulance from this to this. No, there's something else going on. So let's look at what's really happening. Looking at the University of Southampton's Soundwaves page, this image right here, we can see that this side shows what a normal sound wave would travel like. At that sound point where the sound is originating, sound would travel in all directions at a very even frequency. However, if you have something like an ambulance that is moving in one direction, in this case from here to here, what happens is as it moves forward, everything is getting shifted to the right. And so as it all gets shifted to the right, these waves become closer and closer and closer together. And these wave fronts become further and further and further apart. Well, if you have peaks close together, then you're going to have more peaks per second, which means you're going to have a higher frequency. And if your peaks on the other side are further apart, that means you're going to have less per second, which means a lower frequency. And that's why ambulance sirens sound higher as they're approaching you and lower as they leave. It all has to do with their movement and what that does to their frequency.